Up until this point, we have solved two different types of exponential equations. We have solved those where we would turn it into a logarithm, and then we've solved those where we would have the same base on both sides by just looking at it and saying, oh, well, this can be 2 to that and 2 to that, or 5 to this and 5 to that. So we will do one of those options on this, but first, you have some things that need to get out of your way. Like if you wanted to use the logarithmic form, turn this into a logarithm, you would write log base what? 2? Yeah, log base 2, but what are you going to do with your 12 and your 9? They're in the way. We need to move them first, okay? So let's do that. Let's subtract 12 from both sides. That's going to give me 2, and I'm going to have 9 and then 2 to the 3x. And again, we would love to multiply 9 times 2. You can't. Please don't try it. I know a guy that did that. Not worth it. I don't know what happened to him. I just know a guy that did that. He got it wrong. I know that much. I don't know where he is now. And we have 2/9, and 2/9 is a fraction. You can call it 0.2 repeating if you like. I think I will in just a minute just for the sake of explanation with where I'm going with this, but 2/9 is sufficient. Okay, we are ready to put this thing in logarithmic form. This is in exponential form. I do want to point out, based on a chart that you see on the back of your paper, there we go, that'll be sufficient. We'll stop there. A chart that you see on the back of your paper, clearly you'll never see 2/9 in this chart. Even if we extend it back a little bit further, you'll never see 2/9. And again, 2/9 is 0.2 repeating. So in previous videos, I have said, oh, 0.2 repeating, it would happen here. You know, I'd like find the place where it fits. Well, where does it happen? 0.2 repeating is between 0 and 1. So we're actually going to be up here. 0.2 repeating on this side would mean that we have delved into negative exponents. We've gotten into some crazy territory now. Fun stuff, isn't it? Okay, I'd love to delve into that a little bit more, but don't feel like it. Okay, I'm going to take this idea and I'm going to just ignore that that's written there. We're going to convert this into a logarithm. This was just a further explanation. This fraction is equal to that decimal. So there we go. There's that, and that's 3x. And again, we can just ignore all this right there. There we go. And we are going to solve this. So we'll grab a Desmos, grab a calculator, grab whatever, and you type it in. Actually, I've already typed mine in, and I have negative 2.169925. So I'm going to use 3 decimal places and go 170. I'm going to put the 0. Is it wrong if you don't? No. It depends on the class, actually, but for now, no. I'm also going to divide by 3. Let's divide what's in Desmos, or what's in the calculator, by 3, just for accuracy. So we'll divide that by 3 and that by 3. And we're going to cancel those. And we will have negative 0.723, and that is equal to x. Now, if you were to check your answer, you would not get that, okay? You would not get 14 as your answer. If you took your final answer, which was negative 0.723, you plug it in here, you work it out, you won't get exactly 14 because you've rounded it off. We've been through that. Okay, let's go through a few more, and at this point, the problems are gaining a certain level of variety where you need to look at them and say, okay, what do I do? Do I need to flip the paper over and look at the powers? Do I need to try logarithmic form? What do I do? So let's just tackle them one at a time. We'll continue with this next one. We have 36 to the x plus 2, and that is equal to 216 to the 3x minus 1. Okay, fantastic. So logarithmic form, feel free, it works and it's wonderful, but you're going to have variables floating around in all kinds of places, and you'll need to know the properties of logarithms, not the purpose of this lesson, not what we're delving into. Here's what I do notice. 36 to 16, they are on the back side of these notes, and this is where they are. 3, that's not where they are. 6 to the 1 is 6. 6 to the 2 is 36. 6 to the 3 is 216. So then the obvious question is, do we have to memorize this list? And I'm going to say no. However, you do need to be familiar enough with it. I think you should know at least through your cubes. You should know like 6 cubed is 216. Just have some level of familiarity with it to where when you see 216, you're like, that looks familiar. I think that's a perfect cube, you know, that sort of thing. And if you teach math long enough, you'll just know these off the top of your head. All right, so 36 is really 6. Now, up to this point, we have had the lowest possible base on one of the sides already, but now we're going to have to do that for both sides. And that's okay. So again, what we've done previously, not on this slide, what we've done previously was we had a 5 on both sides, or we had a 5 on one side, and we had a 2 on one side, and we made the other side a 2. Well, now we don't have the same low base on both sides. It sounds like I'm talking about a song. We don't have the same low base on both sides. We have lots of trouble. But we do need to get the same base on both sides, not just one side. And that base is going to be 6. So 36 is 6 squared. Don't forget the exponent that you already have. Multiply. 216 is 6 cubed. Don't forget the exponent that you already have. And now, for reasons that we are not going into, we cancel those, and we are left with these exponents equal to each other. Let's go ahead and distribute 2 times x, 2 times 2, 3 times 3, 3 times 1. There we go, and we'll keep solving. Oh, this is going to turn out beautifully. We'll subtract 2x from both sides. That'll cancel those. We'll add 3 to both sides. That'll cancel those, and we are left with 7 equals 7x. I'd like to think that's obvious. Clearly not going to be any rounding error on that one. The answer is just 1. Okay, the next one is a little bit crazy. Okay, the next one's a lot crazy. Let's do it. 1 over 7776 to the x minus 2 equals 1296 to the x plus 4. Okay. We need to get the same base on both sides if possible, and I say that because I'm looking at this and saying we have a variable here, we have a variable here. That's going to be, with our level of knowledge up to this point, that's going to be our first line of attack. So I am looking, flipping the paper over, I'm looking for 1296 and 7776, and I will find them in the 6 column. So here we go. 6 to the 1 is 6. You don't have to write this every time. It's on the back of your paper if you're following along with the notes. 6 cubed is 216. If you multiplied by another 6, you'd have 6 to the 4th, which is 1296. 1296. And then 6 to the 5th, which is 7776. Okay, now clearly there's an issue with this 7776 right here, and the fact that it's in the denominator. We'll tackle it last. So 1296 is 6 to the 4th, and there's an x plus 4, and nobody is mad about that. Okay, we good? I am too. Let's there's multiple ways I can explain this. Let's do it this way. 7776 is 6 to the 5th. Okay, this is what's going on. Now I'm really mad at this thing being upside down, so I'm going to turn it over, and I can do that using negative exponents. Okay, so just side note for just a second. If I had some number, we'll call it a, and we're going to raise it to the -2, that's the same thing as 1 over a squared. Just saying, where'd the 1 come from? It was always there, all right? So negative exponents move things. If I have a negative exponent in the denominator, so if I had like b to the -2 and it was in the denominator, I could bring it up and it would become b squared in the numerator. Where's the 1? There it is. In case you care, there's another 1 there. So I'm going to erase all that in a minute. That's just saying negative exponents move things from numerator to denominator. That has been explained in a previous video. Ask me someday if it doesn't make sense. Let's see if I got them all. Ha, got them all, yeah. All right, so what I'm going to do is move this to the numerator. Totally okay. Now he's in the numerator, and we still have that exponent. And if you want to put this in parentheses and be like, oh, x minus 2, you can. And it's going to take an extra step if we do that, but that's okay. It helps us understand things a little better. And we are now going to multiply these two exponents together. So we have -5 and then x minus 2 and 6 to the 4th and then x plus 4. If you wanted to jump straight from here to here, that would be totally okay. But at this point, I see the same base on both sides. Now, I saw the same base on both sides here, but this one was in the denominator. This is wacky. Let's put them on a level playing field, right? So, whoa, you're going to behave, board. We're going to cancel those. We're going to have -5x plus 10, -5 times -2, and then 4x plus 16, and we'll start solving. So we'll add 5x to both sides. You have to sing it though. We're going to add 5x to both sides. And that gives me 9x here. It's going to give me -6 here. We'll divide by 9. x equals -2/3. There we go, we got it. Okay, there's one more we're going to do in this video, and it looks weird. It looks easy, but it looks weird, and it's just an odd looking little thing. So we're going to scroll this up and talk about E. Okay, not in this class. We don't have to deal with E, but just in case you encounter it, I wanted you to see this problem. E is, from here on out, in your mathematical career, a number. It is not a variable. Okay, so you know how, don't write this down, you know how pi is irrational and it's 3.1415926535 da 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 da, and it goes on forever, and someone one day said, you know, there is no pattern to this, and it goes on forever. Well, E is the same. E is 2.71828, and as I write the next 4 digits, you're going to say, oh, well, it does repeat. Coincidence. 1828. But it keeps repeating, and it does not repeat the 1828. It keeps going, but does not repeat the 1828. Okay, E is a number, just like pi is a number. It is irrational, and we use a special logarithm for that one. You don't have to, but it's handy. So I'm going to do this one 2 different ways. And Desmos knows what to do when you type a lowercase e. It treats it like 2.718281828, whatever comes next. I wish I knew. I wish I knew E and pi both to like 1,000 places. I would be king of the nerds. If you're wondering where E comes from and how it's practical, don't have time for it in this video. But long story short, oh goodness, should I get into it? Yeah, I think I will. Not right now. Anyway, basically, it was created by a man by the name of Leonard Euler. And if you're like, oh, he made up a number, big deal. Oh my goodness, it's super practical. It's used in banking formulas and in all kinds of engineering, and it pops up everywhere. So when you say someone invented a number, someone discovered the practicality of this number. His name was Euler, named it after himself, or maybe someone named it after him. Anyway, that's it. So here goes. I wish you knew where that number comes from. What I want to do is turn this into a logarithm, and I'm going to do it this way this time, but you know, hardcore mathematicians will find me and punch me in the face. So log base E of 70 equals x. And I can totally type that in my calculator. I can totally type it into Desmos, and it will give me the answer. This is method number 1. X equals something. We'll figure it out in a minute. Here's method number 2. Because it is E, it has its own special logarithm. Not in this class. Just wanted to show you this. This is not in your standards, but good to know. It's called a natural log, LN, log natural. It's like a lot of European languages that will put the the noun first and then the adjective. So it's like log natural. It's that kind of thing. We will put a 70 here, and it's equal to x. So you know how if I write the word log, like L-O-G, and I'm just going to make up a number like 7. Okay, if I put log 7, I was like, okay, what's the base? You'd say, oh, it's 10 because it's not written, and you would be right. So if I write ln, I never need to put a base because it's always e. So there's a little e there, not wrong to put it, just, you know, socially unacceptable. You might get shunned at parties if you go to math parties. So I'm going to type that in, natural log, and you can, if you do this in Desmos, you can just type ln, it knows what to do. And I got 4.248. So e to the 4.248 is, rounded off, approximately 70. All right, video is over unless you want to see where e comes from. So here is, well, one of the many places e can come from. Oh my goodness, there's like a zillion of them. But if I wanted to know what that is, what that value is as x approaches infinity. So, and here's a little bit of new notation. Let me not, that looks like natural log. Let me write it for what it is. This is a limit, meaning I'm going to approach something that's a whole different mathematical idea altogether, well beyond the scope of what we're dealing with here, but hey, you asked. The limit, Lim, as x approaches infinity, this is equal to e. So you could try this just for fun, good party trick. You can do 1 plus 1 over 100 to the 100, and you're going to get something, I don't know what, but then you can increase it. Increase this denominator and that exponent, make them the same, of course. And the bigger it gets, the closer it gets to infinity, as if you could ever reach there, the closer it gets to infinity, the closer it's going to get to the actual value of e. So to calculate e very accurately, they would use enormous numbers for that. Not the only way you can calculate e. Love to go into some more of them. Do you want one more? Okay, this part of the video is totally optional. Here goes. If you have a graph that's not crooked, if you have a graph, let's try this. There we go. And you are going to graph the curve. Ooh, that's actually really good. You're going to graph this curve, and this curve is 1 over x. Then, and this is beautiful, absolutely beautiful. We'll put 1 here, we'll put 2 here, we'll put 3 here. Well, if this is 1 and this is 2 and this is 3, and e is 2.7 something, then right about here-ish is e. Then, let's switch to yellow for fun. The area under the curve, but bound between this curve and the x-axis, from 1 to e is exactly 1. So the area is equal to 1. Beautiful. E pops up everywhere. It's fantastic. I love it. I have a whole book dedicated to it. Wait right there, I'll show you. Now I'm just displaying nerdiness. If you've made it this far in the video, you're deep into nerd territory. All right, see you later.